Welcome to day 3. We're going to work even more with related rates, a little bit more difficult word problems and setting up things with more difficult derivatives. So first we're going to look at what we do in geometry. And what we do in geometry is we look at similar triangles. So right now these two triangles are similar to each other. They have the same angles, so the sides are in proportion of each other. So with these two triangles similar to each other, I have this smaller triangle I'm going to outline in pink is similar to this one I'm going to do in orange. That means sides are proportional. So right now I have this side, the left side of triangle DEC, which is 5, over the side here of triangle ABC, which is 25, is equal to, well, this side is x on the smaller triangle over, and this whole side here is x plus 10. Okay, that's setting up my proportionality. I can crisscross here. I get 25x is equal to 5x plus 50. 20x equals 50. X equals 2.5. Okay, that's using proportional triangles to figure out what's going on. So how do we do it for a calculus problem? Well, I have a 7-foot person and a 20-foot lamppost, so that means this side is 20 because that's the lamppost, and this is 7 because that's the person. I don't know any of the bottom side of this triangle, so I'm going to call this side x and this side y. So looking at what I have set up, I have 7 over 20 is equal to, well, side 7 goes with side y, and this whole bottom side is x plus y. So I crisscross multiply. I get 20y equals 7x plus 7y. Bring over the 7, I get 13y equals 7x, or y equals 7 over 13x. That is my equation for finding out the missing sides. So the one thing I do know is that I have a rate. So if the person's walking away at a rate of 5 feet per second, well, let's see. The person's here, and he's walking this way, so that tells me that y prime is equal to not y prime. He's standing here because x is how far he's walking, how is his distance away from the lamppost, so x prime is equal to 5, and I'm trying to find the length of the shadow. How's this changing? I'm trying to find out what y prime is doing. Well, I can just take the derivative of this, and when I do that, I get y prime is equal to 7 over 13 x prime, or y prime is equal to 7 over 13 times 5. So the rate of change of the shadow is going to be y prime is dy over dt is equal to 35 over 13, and this was feet per second. The 16 wasn't really important information. Okay, we're going to work on problems that talk about taking the derivative of a cone. An example, we have a cone over here. We have its radius of the circle base on the bottom and its height of the cone. Here's my formula for volume of a cone. It's 1/3 pi r squared h, and I'm going to take its derivative. And I don't know why I put down chain rule. It's actually going to be product rule. So if I look carefully, I have 1/3 pi, which is not a variable, r squared, and its derivative is going to be 2/3 pi r times dr over dt, and then I have h, and its derivative is dh over dt, or h prime, depending how you want to write this. I do my crisscross. I'll do this way first. So I get dv over dt is equal to 2/3 pi r times h times dr over dt plus 1/3 pi r squared times dh over dt. And if you want to rewrite this as v prime equals 2/3 pi r h times r prime plus 1/3 pi r squared times h prime. And I was like, wow, no matter what you do, there's a lot going on here. You have r, you have h, and you have r prime, and you have h prime. That's a lot to keep track of. There's just too many things. So we're going to figure out a way to make things better for us. So how can I make things simpler? Well, here's my side profile. This is a side profile of a cone, kind of split in half. You know, you have the other half of it. This bottom side is the radius of the base circle, and this side here is the height of that cone. Well, but I also have right here this radius at this point and this height here, and by similar triangles, I have my height over the radius of the cone is equal to the secondary height over the secondary radius. So what I can always do, I have some relationship between the height and the radius. It's always going to be the same. So when I'm done, I'm going to either do height equals some number times my radius, or my radius is equal to some number times the height, and then I could eliminate. I can use to get rid of one of the variables in my equation. Okay, I'm always using this ratio. It's always going to be some ratio, some relationship. Okay, and it's particular for each cone. Let's go through an example. I'm going to move this up. So if I go through this problem, so I'm going to draw, here's basically what a cone looks like, side profile. For what's given to me, I have my radius is equal to 5, and my height is equal to 10. So h over r is equal to 10 over 5, which is equal to 2. So if I bring the r over to the other side, I have height is always 2 times the radius, or my radius is always half the height. I'm going to use that later, because my equation for my volume is, which I gave you earlier, pi r squared h. Okay? Now I have to pay attention to what I'm looking for. I have the water level rises at a rate of 2 centimeters per second. Well, for me, this water level is height and it's a rate, so h prime is equal to 2. That is given to me. And I'm also finding at what rate is water being poured when the height, when the water level is equal to 8. Well, I know my height is equal to 8 at the moment. So I want to rewrite this equation by getting rid of the r. So I'm going to take this, I'm going to rewrite it as v equals 1/3 pi 1/2 h squared times h. And I could rewrite this as v equals 1/3 pi times 1/4 h squared times h, or v equals 1/12 pi h cubed. This is the volume for this particular cone. Not every cone, just this one that we're working with. Then I could take its derivative, and now I only have one input variable. I don't have to do product rule. So when I take this derivative, I get v prime is equal to 1/12 pi times 3h squared times h prime, or better yet, v prime is equal to 1/4 pi h squared times h prime. So this is the equation for the rate of change for the volume, and I can plug in what I know. What do I know? Well, v prime is equal to 1/4 pi. My h was given, which was 8 squared, times my h prime was given, which was 2. And I get my v prime, or my rate of change of my volume. Let's see, 64, 1/4 16 times that. I get 32 pi. And let's see, my units. This was centimeters squared. This was centimeters per second. So my units are cubic centimeters per second. Remember, it's volume, it's three-dimensional. So at the moment when I have this paper cup, when the water level is at 8 centimeters and it's raising at 2 centimeters per second, the volume is changing at 32 pi cubic centimeters per second. Okay, we're back to our Pythagorean theorem derivative, and we have a train that's on a track that is moving in this direction at 0.8 kilometers per minute. Wow, that sounds like a rate. So it looks like it's going this way. I think my x prime is 0.8 along a straight track at a direction shown below, a movie camera. So here's my camera right here. Here's my train moving this direction. And the camera is a 1/2 kilometer away from the track. So right here, this distance y is a 1/2 kilometer. And my y prime is 0 because this distance is never changing. So how fast is the distance? That's my z. How is it changing when the train is 1 kilometer away from the camera? So this height here, this distance here is 1. So I kind of have to use Pythagorean. So I'm looking for z prime. I got to figure out x. So x squared plus 0.5 squared is equal to 1 squared. I get x equals 0.866. So I remember my Pythagorean theorem. And I could plug in what I know. Well, what do I know? Well, I know x is 0.866. My x prime is 0.8 plus my y prime is 0.5. My y is 0.5, my y prime is 0, my z is 1 times z prime. And there's not a lot to do here because this is equal to 0, so I get my rate of change of my z side and my z prime is equal to, these two multiply each other, so I get 0.693, and it's going to be kilometers per minute. So the next thing I want to figure out is how fast this camera is rotating. So I want to figure out how fast that angle is changing. Well, I'm going to use cosine of theta is equal to adjacent over hypotenuse. And the reason I'm doing that is because this adjacent side here, y, is a constant. So at the moment, I have cosine of theta is equal to 0.5, and the hypotenuse is z, or cosine of theta is equal to 0.5 z to the negative 1. So I'm going to take its derivative. Well, the derivative of cosine is negative sine theta, but there's a variable there, so I have to do a theta prime is equal to negative 0.5 z to the negative 2 times z prime, or negative 5 over z squared times z prime. Well, I'm going to come back to this, but I do know z, which is 1. I know z prime, which I figured out already was 0.693. I have to figure out the sine of theta. Well, sine of theta is opposite over hypotenuse, and currently for this triangle, sine of theta is equal to 0.866 over 1. So when I do all this, I get negative 0.866 times theta prime is equal to negative 0.5 over 1 squared times 0.693, and when I divide by negative 0.866, I get my theta prime, or my rate of change of my theta, is equal to 0.4, and it's radians per minute. If you want to convert that to degrees, I would multiply by 180 over pi, and it's about 23 degrees per minute. That's how fast the camera is rotating. Okay, so you see I've set up my problem already. I know the ladder is 13, that's side Z. It's 12 feet away from the wall, that's side X. Side Y that I don't know, so I do a Pythagorean theorem, and I get 12 squared plus y squared equals 13 squared. I do the whole Pythagorean theorem, I get the missing side is 5, so y is 5. I don't know y prime. I know x prime, that the ladder is slipping out at 5 feet per second. And z prime is equal to 0 because the length of the ladder is constant. It does not change. So again, x times x prime plus y times y prime is equal to z times z prime. So I get 12 times 5 plus 5 times y prime is equal to 13 times 0, or 60 plus 5y prime is equal to 0, or my ladder is falling, or y prime is negative 12 feet per second. Then I figure what the area of this triangle is formed. Well, area of a triangle is 1/2 base times height, or particularly for this one, it's 1/2 x times y. Because I have a product rule. Half x becomes x 1/2 x prime, and y becomes y prime. So I'm going to take the derivative of all this. A prime is equal to 1/2 x prime times y plus 1/2 x times y prime. I put in what I know. So a prime is equal to 1/2 x prime is equal to 5, y is equal to 5, plus 1/2 x is equal to 12, y prime is equal to negative 12, and I'll do some simple calculations. I get 12.5 minus, let's see, 144 minus 72. So I do this all, I get my rate of change of my area, or my A prime, is negative 59.5. Let's see, it's going to be square feet per second. That's how the area is changing. So now I have to figure out the rate of change for this angle, theta. Well, I'm going to use sine of theta is opposite over hypotenuse Mostly because I'm going to have sine of theta is equal to y over 13. This is a constant side, as hypotenuse never changes. So when I take the derivative, well, the derivative of sine is going to be cosine theta times theta prime is equal to really just y prime over 13. Well, cosine of this angle in the moment is adjacent over hypotenuse. So in the moment, cosine of theta is equal to 12 over 13. So I have 12 over 13 times theta prime is equal to, well, my y prime is equal to negative 12 over 13. I can move this up. And obviously, to get rid of this, I multiply by the reciprocal. So my theta prime, or my change in theta, is going to be negative 1 radian per second. So when that base of the ladder is slipping out, that's how the angle is changing. So reading through this next problem, let's fill in what I know. Airplane is at 7 miles, so y equals 7, and y prime is equal to 0 because that is never changing. Passes over this radar station. I want to know when the plane is 10 miles, so z is equal to 10. It detects that the distance is changing, so my z prime is equal to 300 miles per hour. I could use my Pythagorean theorem and do x squared plus 7 squared is equal to 10 squared, and x is equal to the square root of 51. So this is the square root of 51. So my x prime I do not know. Again, I could use my Pythagorean theorem. X times x prime plus y times y prime is equal to z times z prime. So square root of 51 times x prime plus 7 times 0 is equal to 10 times 300. So the square root of 51 times x prime is equal to 3,000. And then I get my rate of change of the airplane, which is x prime, is equal to, well, let's see, 3 over the square root of 51. I get 420.1 miles per hour. That's how fast the airplane is flying at that moment. Okay, so here's what I know. I know that I have the height is always 3/8 the diameter. I know that the stand is falling at a rate of 10 cubic meters per minute. That's my v prime. Therefore, if the height is 3/8 the diameter, that means the height is 3/4 the radius, or the radius is 4/3 the height. So here's my volume equation. I'm going to modify that. I'm going to make v equals, I'm going to put in 4 over 3h squared times h. And when I clean that up, I get 16 over 27 pi h cubed. And when I take its derivative, I get v prime is equal to 16 over 9 pi h squared times h prime. The things I know my v prime is 10. I know my h is equal to 4. I'm trying to find h prime because it says how fast is the height changing. I'm looking for h prime. So 10 is equal to 16 over 9, 16 pi over 9 times 4 squared times h prime, and I get, so I move my equation over here and I figure out my dh over dt is 90 divided by 256 pi, which I get 0.1119, and this would be, because it was meters cubed, would this be meters per minute? And it says give it in centimeters per minute, so it turns out to be 11.1 11.1, oops, 11.19 centimeters per minute. Now it asks, how is the radius changing? Well, this where it becomes pretty easy, because I have this equation right here. So r equals 4/3 h. So if I take the derivative, I got r prime is equal to 4/3 h prime, which is going to be 4/3 of the answer I just got. That's pretty messy. So my dr over dt, or my r prime, is equal to 4/3 that answer, so I get 14.92 centimeters per minute. Okay, so I'm trying to figure out how the rate of change on this triangular trough, how it's rising. So I have the dimensions of 6 feet across, 6 feet deep, and 16 feet long. The volume of a prism is just the area of this triangle on the edge here times its width. Well, this width is always 16. That's never going to change. Now when I put water in, the height of the water and the distance across is going to change all the time. So when I get this, I have V is equal to 1/2 the base times the height, which are changing, times 16, which is never changing, so 8 times the base times the height. But for this triangle, for this prism, and in this triangle, my base and the height are the same. So if I ever have, if I'm at 2 feet high of the water, it's going to be 2 feet across, because that's what's going on. The height is 6 and the height is 6 and the base is 6. Man, I can't speak. Okay. So I can use that, and I can rewrite this as my volume is, oh, I'm going to get rid of that. Get rid of that one. I want everything in H. It's 8 times 8 squared. 8 times h squared, because I can get rid of that base, because I'm trying to figure out the height, because I know the height is equal to 4. So what's going on here? Water is being pumped in at 4 cubic feet per minute. So my V prime is equal to 4 cubic feet per minute, and my height at the moment is equal to 4. So I can put all that in here. Well, I got to take its derivative. I take this derivative. I get V prime is equal to 16h times h prime. And I'm trying to figure out the rate of the water, height of the water. So I'm trying to figure out h prime. And I get, I'll change it to purple. 4 equals 16 times 4 times h prime, which is 64h prime, divided by 64. So my rate of change of the height, or my h prime, is equal to 1/16 feet per minute. That's how it's changing. So for this next problem, I know that the balloon is being inflated at 100 pi cubic centimeters per minute. So that's my V prime. I want to know how the radius is changing, so I'm trying to find R prime. When the radius is 5, I take its derivative, I get V prime is equal to 4 pi R squared times R prime. I plug in what I know. I know 100 pi equals 4 pi times 5 squared times R prime. So I get 100 pi is equal to 100 pi times R prime. So I get my rate of change of my radius is equal to r prime, which is going to be 1 centimeter per minute. So my surface area equation, surface area of a sphere is 4 pi r squared. If I take its derivative, SA prime is equal to 8 pi r times r prime, or SA prime is equal to 8 pi times my radius is equal to 5. I just figured out my r prime was 1. So my rate of change of my surface area, or my SA prime, is equal to 40 pi centimeters squared per minute. So there's a lot to this problem. We have a conical filter feeding coffee into a cylinder coffee pot. I know V prime is equal to 18 pi cubic inches per minute. The one thing I do know is that the rate of the change of the volume in the filter is the same as the rate of change going into the, I don't know why I wrote down cone. Should be cylinder. Okay, they have to be the same. The pot is a cylinder. The volume of a cylinder is pi r squared h. This radius is equal to 3, and it's constant for the coffee pot. It's never changing. So I could write the volume as pi 3 squared h, or my volume is 9 pi h. Well, I could take its derivative. I get V prime is equal to 9 pi times h prime. I know my V prime is 18, so I could do 18 pi is equal to 9 pi times h prime. I could divide out by 9 pi, and my rate of change of the height in the coffee pot, or my h prime, is equal to 2 inches per minute. So now I'm looking at the filter, the cone shaped. I know the radius is always half the height. The diameter is 6 and the radius is 6, so the radius is half the height. I could rewrite this as V equals 1/3 pi a half h squared times h. We did this before and we got 1/12 pi h cubed. That is for the filter. I could take its derivative, d dt of all this, which we did earlier. We also know this information here. The height in the cone is equal to 5. I get V prime is equal to 1/4 pi h squared times h prime. I'm trying to find h prime. I know V prime is still 18 pi. Is equal to 1/4 pi times 5 squared times h prime. So 18 pi is equal to 25 pi over 4 times h prime. I can multiply through by 4 over 25 pi. So when I do that, I get my dh over dt, or my h prime, is equal to 72 over 25 inches per minute, or h prime is equal to 2.88 inches per minute. So if you look at this, at the moment, when the height is 5 inside the cone, the rate of change for the height in the pot is 2 inches per minute, because it's a cylinder, but the rate of change in the filter, which is a cone, is 2.88 inches per minute. Okay, thank you for watching.